Well, good evening, everybody, and welcome to the Fish Interface Chapel. It's great to have you here with us tonight. My name is Daniele Struppa. I'm a professor of mathematics here at Chapman University, as well as the Chancellor. And it's a great honor to have this distinguished panel, and it's a pleasure to have you here with us tonight. Chapman, as you know, is dedicated to excellent teaching, excellent research, but also we like to reach out to the community and make sure that the advances that our scholars and scholars around the world achieve are shared with the rest of the community. And so that's really the purpose of tonight's event. Tonight's event is also the kickoff for a major conference that we start tomorrow morning, and this conference is designed to honor the 80th birthday. Can I say the age? The 80th birthday of our colleague Yakir Aharonov, and we are really happy that you're all here to help us celebrate that. Let me talk briefly about the speakers of tonight. Of course, Yakir Aharonov will be one of the speakers. Paul Davies, in the middle, is going to also moderate the event. I want to thank him because it's the second time that he's here helping us in one of these events. Some of you may remember a couple of years ago, Yakir and Paul took the stage in Memorial Hall and presented a discussion on time. So thank you, Paul, for being here again. François Englert, Sir Michael Barrett, and Sir Anthony Leggett. A few words, even though these are names that are world famous, but for those who are not physicists, who are historians or writers. So Professor Aharonov is widely known for his work in quantum theory. The citation for his Medal of Science, the nation's highest scientific honor, says his work in quantum physics, which ranges from the Aharonov bomb effect to the notion of weak measurement, has made him one of the most influential figures in modern physics. Sir Michael Barrett, to his right, is well known for his many fundamental discoveries, including the Barry phase. It's considered the sister phenomenon to the Aharonov bomb phase. He's widely recognized for his pioneering work on quantum chaos and for contribution to a broad range of mathematical physics problems. A couple of years ago, Aharonov and Barry were voted as most likely to win a Nobel Prize in physics in an analysis conducted by Thomson Reuters. Paul Davies, it's a pity they didn't get it by vote, right? Paul Davies' research has focused on the big questions: the origin of the universe, the origin of life, the deep nature of reality, the mysteries of time, and the realm of quantum physics. He is perhaps the most eloquent and clearest presenter of such deep issues to the large public. And he did this in many of his best-selling books and has won numerous prizes. François Englert's work is also widely recognized, and recently the largest machine ever built, the 18-mile-long CERN accelerator in Switzerland, announced one of the biggest discoveries in particle physics in the last 40 years, and the possible confirmation of a long-thought-after particle. The existence of this particle, which serves as a source of mass for most particles, is predicated on theoretical work done by Englert and Braut and independently by Higgs. And finally, Sir Anthony Leggett, world leader in the theory of low-temperature physics, and his pioneering work on superfluidity was recognized with the 2003 Nobel Prize in Physics. Professor Leggett also has made significant contributions throughout his career to the deep questions in both quantum physics and philosophy. The format of tonight's event is that every one of our professors here will speak for a few minutes, and then we'll follow this with a Q&A session. And now I will ask Professor Paul Davies to begin the process of moderation. Thank you.
Thank you. Well, ladies and gentlemen, good evening. It's a pleasure to be back here at Chapman University. Could I get you to turn off your cell phones before we begin the proceedings? We have a little over 1 hour, and I'm going to try to keep to time. The way we will proceed is for each of the panelists here to talk about something at the cutting edge of physics that is particularly interesting to them at this time, and also particularly interesting to the public. We decided that the best way of dealing with this is to go alphabetically, starting with Yakir Aharonov here. So I'll be, Yakir, I'm going to be looking at my watch here and make sure you don't go on beyond your allotted 10 minutes. So without further ado, ladies and gentlemen, I give you Yakir Aharonov.
Thank you very much. I would like to tell you in few words something about the nature of my work that is connected with the main topic of this conference. It has to do with trying to understand more deeply what quantum mechanics is all about. Perhaps you know that at the beginning of last century, there were two revolutions in physics that shook completely all our understanding of nature. One of them was the revolution of relativity made by Einstein, and the other was quantum mechanics that was invented by a number of people. I will mention their names. Now, I will talk about quantum mechanics and try to tell you a little bit about it and about my work connected with that. You know, the big revolution about quantum mechanics was the discovery that nature is not deterministic. That means that you have two things, two particles, say, that start with exactly the same state, they have exactly the same environment, and nevertheless, later they behave differently, for no reason at all. For example, you have two atoms that are in the same state. One of them will emit light after 1 minute and the other after 1 hour, and there was absolutely no difference between them. This looks preposterous. I mean, why should nature behave in such a capricious way? Einstein was, in fact, one of the inventors of quantum mechanics, later became very disillusioned with it, and he said that he doesn't believe that God plays dice. Namely, he doesn't believe that nature behaves in a random way, deciding when this atom will decay, after 1 minute or after 1 hour. Now, when I started to do my research too many years ago, more than 50 years ago, I set to myself a goal, and the goal was to try to understand why does God play dice. I couldn't believe that nature behaves in a capricious way for no reason at all. So after a while, I started to think that maybe what nature is trying to tell us is that there is already a difference between the two particles or the two atoms now, but we can discover this difference only later in the future. So when we do in the future a different experiment that shows that one atom decays after 1 minute and the other after 1 hour, or one of the particles went this way and the other went that way, that information that we find in the future actually has a meaning also before that. It has a meaning that says that already at the beginning the particles knew that they are different, but we couldn't have discovered it by a measurement in the past. So I was able to reformulate quantum mechanics by saying that in the present we should use two information. One information coming from our experiment in the past that propagates to the present, and another information that comes back from the future, like in this movie, Back from the Future, it comes back from the future, and both these informations together tell the particle how to behave. This reformulation led to discoveries of all kinds of new effects and new phenomena, and I will just mention one of them because it's going to be related to what Tony Leggett is going to tell you later. He's going to tell you a story about one cat that was invented by Schrödinger. I will tell you a story about another cat. Or if any of you have read Alice in Wonderland, you know that Alice is coming to this marvelous place full of magic, and she meets a cat there, and she converses with the cat, and finally the cat gets mad and started to disappear. And first the body of the cat disappears, then the face of the cat disappears, and finally the only thing that is left is just a smile. And then Alice tells herself, look, I know I have seen many times a cat without a smile, but what does it mean to see a smile without a cat? Now, this guy that wrote the book was able somehow to anticipate what quantum mechanics is teaching us now. When you look at quantum mechanics in the way that I reformulated it, you find that you can do something like this. You don't do it with a cat, but you take, for example, a particle like an electron that has a property that's called a spin. The electron can be rotated one way or another way, and by doing this kind of experiments that I propose, you can actually send the electron one way and the spin of the electron separated from the electron another way. So I was able to show that it's possible to have a spin without an electron, just like it's possible to have a smile without a cat. Thank you.
Brilliant. And to time. Thank you, Yakir. So next up, to my left, your right, is Michael Barrett. Michael, the microphone.
Thank you. Yes, good evening. I'm going to tell you two physics stories. And this is not cutting-edge physics, and it's not physics that I've done, but it's two stories which I find fascinating, two stories illustrating connections. Physics is about connections as well as about things, and these stories are about connections between physics and other aspects of us as human beings. And the first is about gold, and it's about the color of gold. Now, of course, gold has fascinated and tormented people for thousands of years, and in part that's because of its color, this shiny yellow unique color. And it's a physics question: why is gold golden? Now, it's a physics question because the color of something depends on the light that it reflects and it doesn't absorb. And if you want to understand that, you have to know how the light interacts with the material of the gold. And in fact, it's with the electrons in the crystal structure of the gold. That's a physics question. It's a quantum physics question because the atoms are small and you're looking on a fine scale, and quantum physics is a physics that applies. Now, it's a hard calculation. It's not something you do with a pencil and paper. It's a calculation because the laws of quantum mechanics, as the rest of physics, are expressed in equations, and it's the celebrated Schrödinger equation. And it took a long time, until the 1990s, before people acquired enough skill with computers and methods of computing to be able to do the calculation and explain the color of gold. And when they did the calculation, they got the answer: silver. Well, they'd missed something, of course. And what they'd missed, they soon realized, this was the 1990s, that actually gold is quite heavy. And it means that the nuclei attract the electrons quite strongly, and the electrons move fast enough for it to be necessary to take relativity into account, which wasn't included in the Schrödinger equation. Well, there's another variant of quantum mechanics. Quantum mechanics is not yet compatible with all of relativity. If gravity is involved, then we don't know how to do it. But if gravity is not involved and just things moving fast, then Paul Dirac, who was born actually in the town where I live in Bristol, wrote the Dirac Equation, which is an improvement of the Schrödinger, which works when things move fast. And when that calculation was done, finally, in the 1980s, the answer came out golden. Okay, so this is a surprising thing. It means that to understand the color of gold, you've got to combine the two great discoveries Yakir mentioned of the 20th century, quantum physics and relativity. So I can summarize this little story in 4 words. Gold is relativistic silver. Okay, so that's my first story. My second story is related to our love of abstractions as humans. We're probably the only species that really can adopt and obsessed by abstractions. You might find that surprising, but just think about all the abstractions that you know about. Just words that aren't attached to things. You know, democracy, love, money. If you think money's real, ask yourself, where is the money in my bank account exactly? Okay. Well, another abstraction is music. It's a sequence of sounds which don't have any definite meaning, unlike words, but which affect us very deeply. Now, until about a century ago, if you wanted to hear music, you either had to make it or you had to go to a place where other people were making it. Then came the gramophone, invented by Emil Berliner. Some members of my family think that he was one of our ancestors. I don't believe it, but my mother's maiden name was Berliner, as it happened. He invented the gramophone. Well, that was a good piece of progress, but still it was a cumbersome thing to carry around, or you needed electricity and so on. And the real breakthrough came in the 1980s with the invention of the compact disc player. Now we use other methods, but the compact disc player was the first device you could carry anywhere in the world and make music available to everybody. Now, in the compact disc player, at the heart of it is a laser. Now, that application of the laser was invented in the 1980s by engineers, the laser itself had been invented 20 years before, and although it was a miraculous device, people didn't know what to do with it. Some people here might remember, people were saying, I remember as a student, it's an invention looking for an application. Now, nobody imagined then, the physicists who invented the laser were not the kinds of people who would think of a practical application. That required engineers, and of course in every supermarket your purchases are scanned by a laser. Okay, they didn't imagine that this pure light would be applied 20 years later. Now the laser itself was an application of ideas developed 40 years before that by Einstein. On the way to quantum mechanics, he played a part, as was mentioned already, and one of the applications of these ideas that he was developing was to the way light interacts with matter. Now, he didn't imagine that 40 years later, those ideas he developed will be central to creating the purest light. And of course, they, as I say, didn't imagine that after that, another 20 years, you would have an application. So the compact disc player is a quantum physics machine. Now, with the CD player, and now with the more up-to-date variants of it, for the first time in human history, all the world's music is available to all the world's people. You could be on a mountain, you could be in the desert, in the forest, on the sea, and you could hear perfectly reproduced music. So the 5-word message of this little story is, quantum physics has democratized music. Okay, thank you.
Well, thank you. Thank you very much, Michael. That was fascinating. In addition to being moderator, I get to have a go myself at telling you something that is interesting me. And it's a problem that will be well known to many of you here because you often read about it in the newspapers as one of the great unsolved problems of physics. So one of the biggest discoveries, maybe the biggest of the last century, was that the universe is expanding. So it's getting bigger all the time. So if you run the great cosmic movie backward, then it would have been smaller in the past. And if you extrapolate that back some billions of years, then it seems that the whole universe burst into existence some billions of years ago. We now know that it's 13.7 billion years ago. And we know that the universe is expanding because we see the galaxies rushing away. And we know it was once very compressed because we still see the heat radiation filling the universe like the fading afterglow from the Big Bang, which is the term we give to this explosive origin. Now, why was it explosive, this origin? Well, we know from daily experience that gravity is a pulling force. It keeps our feet on the ground. And in cosmology, there's only really one force that matters, and that's gravity or gravitation. So it's a pulling force. So it makes sense to think that as the universe expands, it slows because the effect of gravity is to restrain the outward rush of the galaxies. And when astronomers began investigating this some decades ago, it did indeed seem that the universe was slowing down over time. And that means that, of course, it must have started out expanding much faster, hence the Big Bang. And this state of affairs continued right up until about 10 years ago when, much to the astonishment of astronomers and physicists, it was discovered that the expanding universe is now picking up speed. That is, it's been slowing for some billions of years, but it's now accelerating. It's expanding faster and faster. This caused total consternation as to what this anti-gravity, this repulsive force was that had seized control of the universe. So we now think of the expanding universe as a sort of gigantic cosmic tussle between two different forces, the forces of attraction and the forces of repulsion. The force of attraction is good old-fashioned gravitation, but what is this repulsive force? Well, we don't know, and so when physicists don't know something, they tend to give it a sexy name, so it's called dark energy. So you'll read in newspapers that dark energy is one of the great unsolved problems of physics. What is it? Now, I've always thought that the mystery aspect of this is a little bit overdone, because as long ago as 1917, Einstein suggested something just like this. He was a theoretical physicist, and so he wrote down the equations. Michael was just saying about the theory of relativity in its complete form, the so-called general theory of relativity, which was presented in 1915, contains the equations of gravitation on the left-hand side, and on the right-hand side is the sources of gravitation, like the mass and the energy of the universe. But he realized that there was an optional extra term that he could put in. He called it the cosmic term, and it had a type of repulsive effect. And if you ask, what is this term physically? Well, it's just the energy of empty space. And you might think, well, why should empty space have any energy? Because it's empty. And my answer to that is, why not? After all, you can't pluck a bit of empty space out of the universe and put it on the scales and weigh it. It's all around us. Space is all around us. So if space itself has energy, there's no way we would know except looking at the universe as a whole. And when we look at it as a whole, and it's picking up speed, expanding faster and faster, it's clear that that even empty space has a type of energy. Now, normally energy is gravitationally attractive, but it turns out that if it's the energy of space, for reasons I won't go into, but having to do with the symmetries of space and time, that has a repulsive effect. So a simple answer to what is dark energy is it's just the energy of empty space. And this is where it gets really interesting, because in quantum physics we have a good reason to suppose that empty space should have energy. And the reason is that there's a lot of quantum physics being discussed here, but one of the fundamental principles of quantum physics is Heisenberg's uncertainty principle, and it says, roughly speaking, that if you know where something is, you don't know how it's moving, and if you know how it's moving, you don't know where it is. So if you imagine a little pendulum, if you say the pendulum has zero energy, it's just sitting inert with the little ball below the pivot, well, that works well in daily life, but in quantum physics, you can't do that, because if you know that the little ball is directly below the pivot, you don't know how it's moving. And if you can say it's absolutely still, you don't know where it is. Either way, there must be some energy. We call it zero-point energy. Now, it turns out that all of the fields we know in nature, and the electromagnetic field is the obvious one, they all have zero-point energy in every one of their modes. And so you can say, well, suppose we add up all these little bits of Heisenberg uncertainty energy, all this zero-point energy, for all of the modes of the electromagnetic field. What do you get? Well, first calculation, you get infinity. Well, that obviously doesn't make any sense. And then you think, well, can you put in some sort of cutoff in the total amount of energy? And the answer is yes, when it becomes gravitationally very important, then that would be a good point to cut it off. And if you do that, you come out with a number which is spectacularly bad. It's 122 powers of 10 bigger than what the astronomers have observed. So we have an explanation for what this dark energy is. It's the energy of empty space associated with the quantum vacuum, or the quantum zero-point energy. But we're out by a factor of 10 to the 122. Stephen Hawking has called this the greatest failure of theoretical physics in history. So I think we're on the right track, but we clearly have some work to be done. And so I'm going to leave it as an open question as to how we can continue to get energy in empty space, but suppress its value by this stupendously large number. So that's it from me. and it's now my job. Now my job to hand over to François Englert, who will talk about something completely different.
Yes, to begin with. Okay, so, well, you know, the discovery of a particle at CERN has made its way much outside the realm of, or the community of physicists. But I would like to try to explain why this is an important effect. And unfortunately, to do that, we should go back to the history of physics, and I will therefore summarize the history in physics probably in the first minutes, if everything goes fine. Right. So, what is physics essentially? Well, the way we understand it now, it's essentially a way to try to interpret the obvious diverse phenomena that we are living into as particular manifestation of general laws. For instance, as everybody has heard about Newton's law, we know that falling objects or the revolution of planets or the tides essentially are consequence of the Newton gravitational law. But thing goes fast. Essentially, this idea that one can understand in terms of general law, general testable law, the different manifestation of it is rather recent in the history of mankind. Essentially, it comes from the Italian Renaissance. And from there, things went very fast. And they went so fast that in the half of the 20th century, in the first half of the 20th century, one could imagine that we could take into account that we could essentially interpret the totality of phenomena from the level of the atom to the edge of the visible universe in terms of two known laws, and only two. One is general relativity, which is the generalization of Newton's gravity, which I just mentioned, and the other is quantum electrodynamics, which is the generalization of Maxwell's theory, which was a theory which explained light and not only light, but essentially all the electromagnetic forces and the light. Now, when I say you can imagine that you can understand everything in terms of that, of course that doesn't mean that you just take the equation and you find out what it is. But you have to do a lot of work to understand this, the way it works. But nevertheless, in principle, this is true. But there was a big problem which was not solved. The electromagnetism and gravitation are long-range forces. By that one means that they act on objects no matter how fast they are from each other. But clearly, when we apply this to atoms, we have first to suppose that there are atoms. The atoms have nuclei, and that is very small object. And we know that just the fact that they're all together, that they are radioactivity thing, means that there must exist short-range forces. And short-range forces means that there are forces which act on very small distances, and we don't feel them at our size. How come? So that is what we, Braut and myself, we explained in '64. And I cannot explain in detail, of course, but to give just a general idea. The general idea is this, that there is in the world something like a field. What is that, a field? Think of a ferromagnet. That is, a ferromagnet has a magnetization, which means there is a magnetic field, if you wish, which is inside a magnet, which can be arbitrarily large. Well, the basic idea is that the universe is embedded into such a field, with one difference. The magnetic field and a magnet has a direction, which is magnetization, where this field clearly cannot have a direction because we live in a universe which has no preferred direction. So this means that the field has no direction. That is called a scalar field. And this is like a sea now which embeds the whole universe. Right? And what happens is that some of the particles, like the photon, which is the constituent element of light in quantum theory, the photon essentially mediates, by being exchanged between two particles, mediates the electromagnetic forces. That's how quantum mechanics understand the effect of the electromagnetic forces, electricity and magnetism. Now, if we now invent a set of photons and put them in this sea, then they have some difficulties to travel because they are like fish in the sea, and that doesn't go as fast as a bird. And so they go very slowly, and because they go very slowly, they can't go very far, and the forces that they can mediate are only at very short distances. That's how it happens. And because of the C, short-range forces can exist like this. And also, more generally, actually, elementary particles, which would, in the first instance, have no mass, can acquire mass also this way. So that's essentially what happens. And that's what we invented, and it turns out to be right. How do we see it's right? Well, you can't measure this C itself because we are embedded into it and it's everywhere, so it cannot. But C has waves, right? Particularly here they are big. But, so there are waves, and waves, of course, there are waves inside. We don't think about the surface because there are no surface. But a little bit of imagination, there are waves inside. And these waves, quantum mechanically, are always composed on some particles. And therefore, one cannot detect the C, but one can detect the little perturbances, which is composed of particles, and that is what has been detected at CERN. Therefore, it's a direct proof that the whole picture is right. So that explanation, of course, is very crude, and if you believe it too much, then I warn you that it's not as simple as that. But thank you.
And a truly fascinating time to be a theoretical physicist who has connected with the real world of experimental physics. And not many occasions when that happens in the history of physics in such a profound phenomenon. So we're all very thrilled. So last but certainly not least, Tony Leggett, who will return to the quantum theme, I believe.
Well, most of you probably know that, or have experienced, that if you take a fairly random group of people off the street and set them to discussing some issue in, say, politics or the social sciences, quite likely that things will get rather animated and excited. Thank you. People get quite animated and excited, and in fact, in some cases, there may be spectacular outcomes of such discussions. But you might think that if you took a group of physicists in the year 2012 and got them discussing some kind of technical issue in physics, that kind of thing really would not be likely to happen. After all, for something like 90 years now, with the possible exception of some of the issues in cosmology, such as Paul Davies has talked about, physics has really, in some sense, been in a rather calm phase. Those of you who are familiar with Thomas Kuhn's work on the history of science might remember that he divides the history of science into what he calls normal periods and revolutionary periods. And crudely speaking, the normal periods are the periods in which the sort of questions you're allowed to ask and the sort of answers you're allowed to give to them and the kind of evidence you're supposed to provide in favour of those answers, all of these things are pretty much agreed in the relevant community. And as I say, with the possible exception of some issues in cosmology, I think it's fair to say that has been true in physics for much of the last century. So you might think that it would be impossible to generate the kind of excitement or animation that you get from getting people to discuss politics and so forth. Well, there is one big exception to that rule, and when I was young and mischievous, I used to occasionally go to parties at physics conferences and lob this question like a hand grenade into an innocent group of physicists and stand back to watch the fun that ensued. What is this, this special question? Well, crudely speaking, it goes something like this. What we call quantum mechanics was invented crudely speaking, in the mid and late 20s. Quantum mechanics is not just a new theory, it's really a whole new way of looking at the world. Over the past 90 years or so, it really has explained an awful lot of things about the physical universe. It's explained them, as François Englert told us, from the level of the smallest, or the finest scales of elementary particles to the largest scales that we know in cosmology. And at the moment, right now, we have no, as far as I know at least, we have no firm experimental evidence that it ever goes wrong. So what's the problem? Well, the problem is that if we take seriously the idea that since presumably big things like this glass or the table or my brain or whatever, big things are made of little things. We have a theory which explains brilliantly the behaviour of little things, then it should, at least in principle, we should be able to apply that theory also to the big things made of them. That's where the problem starts. And in some sense, the physics community cannot really even agree on whether it is a problem or not. Many people think it's entirely trivial, and that the relevant questions have been solved long ago and one simply shouldn't waste time on them. Some people, that happens to include me, believe that this is a very, very deep problem indeed, and some people, not including me, would even say that you really shouldn't go on doing physics as we're doing it until you've understood the resolution of this problem. Now let me try to say a little more in detail about what the problem is. Suppose we have a set of microscopic objects like, say, electrons or atoms, let's say atoms for definiteness. Suppose that these atoms are faced with the choice of they have to go from A, say, to E here. They can go two ways. They can go this way, or they can go this way. Okay? Now, you might think, first side, that each individual atom would have to make that choice. It would have to decide either to go this way or to go this way. And indeed, if you actually set up a sort of inspection booth to see which way a particular atom went, indeed it does seem to make that choice. Every time you, as it were, ask it the question, did you go this way or this way, it tells you one or the other. Never both, never neither. However, if you don't ask it, if you don't force it to make the choice, if you don't set up some kind of customs booth for it to have to go through, then the experimental results make it look very much as if it didn't go through one path or the other. The technical name for the experimental results which lead you to this conclusion is interference. Some of you might have had some experience of interference of light, say, in laboratories. It's essentially that phenomenon. Looks as if, as it were, something is coming through both of these paths. And that something is associated with each individual atom which goes through. Now, in some sense, we don't know, or at least most of us don't claim to know, what that something is, but at least in quantum mechanics, it has a representation in the formalism. The representation is called technically an amplitude, and when we get this situation, we say that quantum mechanics assigns an amplitude to each of these paths simultaneously. Now, how you actually interpret that is a delicate matter. Do you say each individual atom goes through both paths, or it goes through neither path, or the whole question doesn't even make sense and shouldn't be asked? Say any of those things. However, the one thing apparently you can't say is that each individual atom definitely chose one path or the other. So far, so good. And, I mean, that seems rather weird. It seems weird that, for example, atoms should behave differently depending on whether you look at them or not. But in the 30s and 40s, the great Danish physicist Niels Bohr convinced most of the physics community that there was really no great problem here. And crudely speaking, he said there was no problem because, look, you shouldn't even think of microscopic objects like atoms as even possessing properties in their own right. They're only in some sense a link between some kind of macroscopic, that's sort of everyday level, preparation device and some kind of equally macroscopic observation device. And apart from that, they have no reality. So it's natural that the behavior of an atom should depend on the macroscopic setup, the everyday level setup, the series of devices and flashlights and so forth that you use to look at it. Niels Bohr was extremely prestigious in the physics community, and he managed to convince much of that community that there was really no mystery here. One of the people he didn't quite convince was another very famous name in the, among the founding fathers of quantum mechanics, Erwin Schrödinger. And Schrödinger was very worried by Bohr's resolution, and he finally, in 1935, formulated his worry in the form of a very famous thought experiment. The thought experiment in question goes something like this. Suppose that we make a setup, and there's no reason why we shouldn't, as far as we know. We make the following setup. We have an atom which, again, can take two different paths. We have a set of atoms which can take two different paths. But let's just imagine that the first atom, which, we somehow ensure that the first atom which comes out definitely takes, say, the left-hand path. Then, basically, it goes away harmlessly and nothing spectacular happens. Suppose, on the other hand, it takes the right-hand path. Then, rather than recombining the paths, we make the following arrangement. We arrange that that atom enters some kind of counter, and when it enters the counter, that will trigger some electronics. All these is sort of pretty standard stuff, which is no reason to think we can't do it. It triggers some electronics, and as a result, various things, various everyday level. I shall sometimes use the word macroscopic here, and that simply means, crudely speaking, at the level of everyday life and everyday observation. Okay? So at the everyday level, lots of things happen, and in particular, a hammer falls upon a box of cyanide inside a closed box, whose other occupant is a cat. This is the famous Schrödinger's cat. So that if the atom does indeed come this way, the result will be the death of the cat inside the closed box. Well, what's the point of this bizarre setup? Well, in quantum mechanics, it's a very firm principle that if some initial state, let's say A, leads to a final state A prime, and an initial state B leads to a final state B prime, then if we have in the initial state, if both these amplitudes are represented, then in the final state, both the amplitudes, the corresponding ones must be represented. In other words, if the amplitude for A to happen is non-zero and for B to happen is simultaneously non-zero, then at the end of the day, the amplitude for A prime to happen must be non-zero and simultaneously the amplitude for B prime to happen. But in this case, you see, A is a state of the universe in which nothing spectacular has happened and the cat is still alive and sitting up and mewing happily. B prime, on the other hand, the final state, is a state in which the cat is dead. So we are forced to the conclusion that if we prepare the first atom which comes out of this bizarre apparatus in a quantum, so-called quantum superposition of A and B, that is a state in which both the amplitudes for A and B are non-zero, then we're going to end up with a final state of the universe in which the amplitude for the cat to be alive is non-zero, and simultaneously the cat for her to be dead is not non-zero. Now you see, when we had that situation at the microscopic level, we were forced to say the one thing we can't say is that one or other of these two things happened. So now what's the state of the cat at the end of the day? Are we forced to say that she is neither alive nor dead, or that she's in some kind of weird combination of being alive and dead? Well, we all know, I mean, luckily the animal protection societies have prevented us from doing this experiment in a statistically meaningful way, but rather few of us doubt that if we were to do it and we were to take the lid off a particular box, then that particular cat would be one or the other. We would not even know how to recognize this weird situation in which she's neither one or the other. Okay. What's going on here? There's a huge debate in the physics community about whether this is a real problem or not. Those who hold it's not a real problem usually rely on a phenomenon that goes on a technical name of decoherence, which basically says that the effect of any kind of interaction with the outside world is going to spoil the interference effects. So in some sense, the evidence that something weird is going on will have gone away by the time you come up to the level of a cat. And I think most of us, including me, don't doubt that technically that is a correct statement. You would not be able to see directly the effects of interference between the living and dead state of the cat. Does that mean, however, that you can suddenly reinterpret the quantum mechanical formalism to say that one or those things or the other has happened? So that's, as I say, that's the question which really generates the controversy and the animation among physicists. Until about 25 years ago, it seemed that this is probably one of those questions which physicists would tend to describe as philosophical, meaning, philosophical in the language of physicists tends to mean questions to which they can't foresee any experimental input, which therefore are best left to other people, as it were. Over the last 25 years, however, it's turned out this is not necessarily the case. It turns out that one can go at least a certain way towards the everyday level and try to test whether quantum mechanics is still working or not, whether you still get this weird phenomenon. Crudely speaking, what you've got to be able to do is to somehow shut off the effects of this so-called decoherence, this spoiling process, and so ensure that you can still see interference phenomena at some kind of level much higher than that of the individual atom and much closer to our everyday world. And over the last 25 years, and in particular over the last dozen or so years, people have got very, very good at doing this. We can now do experiments with superconducting devices which involve, okay, they're still not, I mean, people could argue a lot about whether these are really at the everyday level or not, but I think there are rather strong arguments, actually, that they're at least as much at the everyday level as, say, the distinction between the two states of a small dust particle which can be resolved with the naked eye. As I say, the argument gets very technical at this point, but I think there are rather strong arguments that it is that far. So in fact, so what have we seen? Well, so far at least, quantum mechanics seems to be still working quite fine at this kind of level. And that's sort of worrying because eventually we are going to be able to presumably go further. We're eventually going to be able, perhaps in 50 or 100 years' time, to test whether quantum mechanics is working, say, for the elementary stage in the human physical process. And actually, at the University of Illinois, my home university, we are actually, some of my colleagues are actually starting an experiment which will try to confirm what everyone believes, that the human perceptual system responds to these weird quantum superpositions in the same way as inanimate measuring devices do. Apparently, as far as we know at least, that has never been tested experimentally, and no one really, I think none of us really believes with any confidence that we're going to get anything weird coming out of this, but at least it's a first small step along this road. But I certainly think that in 50, 100, 200 years' time, assuming that nothing else has come in and says that our whole picture of the world is wrong, that may happen. I would actually give it quite a strong chance of happening. But if it doesn't happen, then we're going to have to worry quite seriously about this paradox of so-called Schrödinger's cat at a level which is really quite uncomfortably close to our own human consciousness. And I think that's really a very, very intriguing prospect. Thank you.
Tony, I once did a TV show trying to reenact Schrödinger's cat experiment with a real live pussycat from the studio. Very docile animal, but by the time we'd done like the 5th or 6th retake, this poor cat was totally neurotic. Anyway, never try it with a real cat. So we've covered a lot of territory with a strong quantum theme, as befits 80th birthday meeting for Yakir Aharonov, who has done so much to bring quantum mechanics, which, as you heard, began, well, its origins go back to the turn of the century before last, to about 1900, but was developed mainly in the 1920s and 30s, and has done so much to bring us into the modern era with various new tests that can now be done, tests of what were previously just thought experiments. So now I think the time has come to turn this meeting over to you, the audience, and give you an opportunity to ask some questions. Because it's been such a broad sweep, I think we could probably entertain questions on almost any topic in physics. I think we should steer clear of politics, perhaps, particularly theoretical physics. And so what I propose to do is to just sort of take one from this side and one from that side, and we'll keep going until we run out of time. So could I ask for a show of hands? And if you could direct your question to an individual, then that would help. Gentleman here in red. Yeah, we have microphones both sides, so and if there's someone on this side who's itching to ask a question, they could be making their way to the microphone in anticipation. Oh, yeah, and questions only, please, not statements or theories.
I've been a teacher, so I can talk pretty loud. I'm probably missing something on this accelerating expansion of the universe, but,
me, right.
But the question is, does this mean that at some time in the future all the matter in the universe will be rushing away from all the other matter at the speed of light?
Right, so this is a question that comes up all the time, and it doesn't have to be sometime in the future. Right now, as we look farther out into space, we see the galaxies more and more redshifted, and if you interpret redshift as a sort of velocity of recession, then already we see galaxies which are so far away they're on the edge of receding from us at the speed of light. This is not a problem. You have probably read that Einstein told us nothing can go faster than light. What he meant was that one object can't overtake another faster than light. And that remains true. But it simply doesn't apply to the expanding universe, where these objects are spatially very separated and where the space in between is expanding. The best way of thinking of the expansion of the universe is not the rushing away of a lot of galaxies from a common center, but as the swelling or stretching of space itself. And you might think the idea of space stretching is bizarre. This was the key contribution that Einstein made way back in 1915. Well, it's easier somehow to think of space being curved, and you can see the wonderful pictures of what are sometimes called Einstein rings, arcs where the light of a very distant galaxy has been bent and smeared out into an arc by an intervening object. And so we can see with our own eyes, we can see space being bent. Well, it's one next step to it being to its stretching. And so think of the expanding universe as the stretching of space, then there isn't any conflict with this speed of light thing. Now, gentleman on this side.
First, thank you, or happy birthday, Yakir. And thank you for putting on this event tonight. Thank you to everybody on the panel. But my question also has to do with cosmology, and so directed to Paul Davies. Yeah. Big fan, by the way, of your books.
Thank you.
Actually, there's two questions. I'll keep them short. Fine. You mentioned the Nobel Prize in Physics, excuse me, for discovering the accelerating universe.
Right.
1998. I'm wondering, first of all, why did the Nobel Committee overlook the work of James Gunn in 74, 75 when he wrote his paper on the accelerating universe? And then secondly, the issue with the energy of empty space or near empty space seems to me to be possibly exaggerated. It seemed to my mind that that energy should be trivial or almost trivial. why not think of that expansion coming? We have relic radiation. Why not think of that as relic kinetic energy from the expanding universe, and the acceleration coming from the bounds of gravity kind of slipping away?
Right. Okay. So first question, I don't know about the deliberations of the Nobel Prize Committee, but from what I recall of the paper by Gunn, it was not based on the same set of observations as the type 1a supernova results that have been published. And so I think in retrospect, that paper does not offer convincing evidence that the universe is accelerating. I think that the distance of the objects simply didn't go out far enough to be able to make that. But I have no idea what goes on in the Nobel Prize Committee. But the second one, what we're after is, of course, something to make the universe expand faster and faster. And when you say a weakening of gravity, well, that's in effect what we're talking about. The so-called cosmic term in Einstein's gravitational field equations has a gravitationally repulsive effect. So the energy of empty space has that gravitational repulsive effect. The energy of ordinary matter has a gravitational attractive effect. The way they vary with distance is different. So the gravity of the sun diminishes famously like the inverse square of the distance from the sun, whereas the anti-gravity effect of this empty space increases with distance. And so, in a sense, the energy of the empty space is weakening the effect. That's exactly what's happened. And now it's not only weakened it, it's overwhelmed it, and it's the dominant force, that attractive force. But they vary differently with distance. So it's not just a matter of saying gravity gets weaker over time, but retains this inverse square effect. It's quite different from that. It's a different type of force with a different relationship with distance. Right. So much for that. So I hope we have a question now for somebody else.
Yeah, I have a question for Dr. Aharonov. You talked about two identical atoms in the same excited state, completely indistinguishable, but this one decays in 1 second and this one waits a minute to decay. Are they in fact identical, or are they different in some way that we may not understand yet?
Okay, the question is really whether there could be some hidden differences between them that we don't recognize yet and we may recognize in the future. In fact, my physics advisor, Professor David Bohm, invented the theory, showed that it's possible to explain all of at least non-relativistic quantum mechanics by assuming that there are indeed hidden variables in each atom, and they will tell each atom when to decay, and we simply can't measure them yet. But then came Bell and showed that if such hidden variables do exist, it's possible to show that their interaction will violate relativity. So if you A, believe that relativity is true, and B, that those hidden variables are not just a mathematical construction, but eventually they have physical meaning, then you come into a contradiction, and therefore people decided that they don't like that idea of hidden variables, and they say that indeed these atoms are exactly identical from the information in the past. What I propose is that when finally we make an experiment that distinguishes between them, we find the difference between them, and then the question is whether this difference has relevance already before or only after. And I suggest that it has relevance before, and in that sense, we find that there is indeed a difference between them in this reformulation.
So every atom may be different?
Yeah, okay. If you believe that things come back from the future and so tell them that they are different, then they're always different now. Okay, but we can't find this difference by experiment that we do in the past, only by experiment that we do later in the future. Okay?
Thank you.
So no more questions on the left wing here.
I have a dark matter question. Why do physicists think that the dark matter is influenced by the weak force and not just by the gravitational force.
Right. Incidentally, dark matter is not the same as the dark energy I was talking about. François, do you want to get that one?
No, I didn't understand exactly the question.
Yeah. Why do physicists think that dark matter is influenced by the weak force and not just merely by the gravitational force?
No, I think, well, first, to be clear that the dark matter is not the dark energy,
Yes, I know.
right? It's something different. And for the moment, one doesn't know what is the origin of dark matter. There is a...
I'm having trouble hearing.
Oh, there is a leading idea is that it's due to some particle which has not yet discovered and which are to be discovered. That's one possibility, and probably the most, probably the best possibility. But we cannot exclude it. As long as it's not really discovered, one cannot exclude whether it's this or whether it is something that is a change of gravity. It could be. For the moment, we don't know. But certainly, there is a hope that that question, at least partially, could be settled in the LHC, because it is possible, after all, that one would discover such particles which interact weakly, sufficiently weakly not to be detected, and are present. And of course, that doesn't mean that it's not detectable. If not, you would never find it. But it should be detectable, but relatively stable, and probably stable, and things like this. But we'll see.
If I could just add a little postscript, there certainly are people who propose that dark matter might just be gravitationally only interacting. They call, for example, sterile neutrinos. These would be neutrinos which would have, wouldn't interact with other weak force, but only the gravitational force. And then that's the problem with that theory. It's unfalsifiable, pretty much. Okay, question on the left.
My question takes us back to quantum mechanics. One topic that engenders debate among physicists now is the nature of the quantum mechanical wave function. Is it a physical object, or is it just a catalog of the information that we're able to know about a particle? I wonder if you can express your opinions on this debate.
Yakir has written this wonderful book in which he addresses that very issue in one of the early chapters. Is that right? Would you like to take that question, Yakir?
Well, I believe that the quantum wave function is a physical object, but the way to see it is only if you have many particles that are described by the same wave function, then you can do a new type of experiment that I call weak measurements, in which you can actually measure exactly this wave function without disturbing the particles at all. But you need for that to have many particles that are described all by the same wave function.
Would the other panelists like to add anything? Tony, is it real? Psi? Can you kick it?
I think my answer to that would depend rather heavily on the answer to another question, which is quantum mechanics really the whole truth about the physical world? If the answer is yes, then I think I would take the view that it is merely a sort of catalogue of information. If, on the other hand, the answer is no, then I think one does have still a freedom to assign a physical reality to the wave function, although I don't know how to do that in detail, but at least the possibility is open, I think.
Michael, do you want to add anything? No? No?
Well,
gentleman here.
If the entropy is give the arrow of time, when a system is in equilibrium, there are fluctuations in the entropy, so the time go back and forth in that system.
Sorry, what is the question?
Since once the system is in equilibrium, still there are oscillations, so it goes to the maximum entropy and going down again. And since the entropy is the direction of time, the time is oscillating in that system.
I think perhaps, are you confusing the arrow of time, the irreversibility or the directionality of processes with time itself? Of course, things will still happen even in equilibrium, but there's no directionality.
But No, I don't think I am confused. I think the arrow of time, it gives the direction of increase in entropy.
Right, and then if you reach a maximum entropy state, then that doesn't mean that time ceases. It just means that there's no directionality to the physical process.
No, but then the entropy goes down for a fluctuation.
Well, if you wait a long time, yes, yeah, that's true. Of course, there will be fluctuations.
No, it's in a gas in a box continually fluctuating. Cannot be always at the maximum entropy.
Correct, yeah, there will be fluctuations around that. So, famous example being Brownian motion. Boltzmann, of course, proposed in the 19th century that the reason that we live in a universe which is very far from thermodynamic equilibrium is because after an immense period of time it fluctuated into this present state. I don't know anyone who still believes that as an explanation. But you're quite right, but I'm not sure that... we've had an interesting discussion, but did you actually ask a question?
Well, the question was, since you agree that there are fluctuations, of course everybody agree with that, the arrow of time, when the entropy goes down,
yes,
go in the direction of the...
goes backwards, so to speak, yes.
Well, it's not that something it bothered me a little. Probably nobody bothered that for that, but it bothered me. That the arrow of time, it don't keep in the same direction. It go in the opposite direction. Then come back
right,
continuously oscillating.
Right.
Why this could be I just finished reading a book and they saw hook and the arrow of time when it's not something permanent. I mean...
this is a very deep subject and we could be here a long time if we were to go into all different aspects of that. But rest assured that we do understand what's going on here. So now we'll flip to the...
This is a non-physics question.
A non-physics
question. But it has to
right,
do with physics
not
research.
Politics. Okay.
Well, right, I think we can't separate the two.
Right.
And this is my question because you've now reminded me why I majored in political science as opposed to physics. Right. What I do know is this, and this is my question. The broader question is, does it matter where physics research takes place?
Where?
Well, let me explain the question more. In the 80s and 90s, the United States Congress appropriated up to $2 billion for a super collider conductor to be built in Texas. They spent $2 billion and another $500 million shutting it down. And then we put the research seems to be taking place in CERN, where we just saw a major breakthrough take place. In terms of just physics research, does it matter that the discovery took place in CERN, or would it have improved things for the United States if it took place here? Or is location not an issue when it comes to research?
Right, right. I'm sure that everyone on this panel will have something to say about that. I certainly don't want to dominate the discussion. I could say something. Tony, you've moved, like I have, from the UK to the US. Does it matter where you are, who does the work?
From the point of view of I think from the point of view of physics, it doesn't matter a bit. Right. From the point of view of politics or economics and so forth, it may matter quite considerably, I think.
Yeah. Tell me why.
Sorry?
Why does it matter for the average American that the breakthroughs are taking place in Europe as opposed to the United States?
May I respond to that?
Is it just bragging rights, or does that have practical implications?
The idea is that while you do this research, what is important not that the final discovery, but there are lots of technical developments that happen while you do that are extremely important. And therefore, if this research would have been done in the United States, there would have been a lot of rewarding side discoveries that are now being done elsewhere, and that helps the economy of the United States finally.
Michael, would you like to say something?
Yeah, I think it doesn't matter at all. You take a historical view. The the sort of baton of science discovery, think of it as a relay, has passed from one country to another. I mean, it was the Greeks beginning, and then in the Islamic world, in the Middle Ages, discoveries were made, and then that stopped, and then it still hasn't started again there, and then it became the Renaissance, and then America was predominant, and it really doesn't matter. I mean, the discoveries, certainly now, the world is so connected that discoveries made in one place are known instantly elsewhere, and I think, I'm not quite sure I agree with Yakir on this, that the spin-offs could occur anywhere. I mean, think of the technologies that developed, for example, in Japan as applications of fundamental science, which wasn't discovered there. I mean, it can happen very quickly. The world is very much more connected than it used to be. So the answer, I say it again, I don't think it matters at all.
Okay, finally we have a disagreement between the panel. Okay, what I meant is not that the final discoveries would be transferred to other places. Certainly it happened. But why, if this thing was about the United States, you would have many people, more people trained in all these things in the United States, and now these people are trained someplace else. They are not in the United States. So the United States is missing all the developments that would have happened here. There would have been a huge amount of money going into training many young people to do all these things, and that happens now in CERN instead of the United States. Is this point acceptable? Okay.
So that's the problem about asking questions of politics, you see. We have time for one last question, if there's someone who wishes to ask it. This gentleman here.
I wish to say happy birthday to Dr. Aharonov, and my question is directly
That's
to
a question, or?
Yeah, could you come a bit closer to the microphone, please?
So, matter has different states, like being insulator, conducting, or superconducting. And these are all due to the different arrangements of the elementary particles inside the matter. So, is consciousness also can be described as the state of matter using physics? Thank you.
Yes, well, so when I said no politics, I was thinking of saying and no questions about consciousness either. Because we could be here for a very long time. Does anybody on the panel have like a one-sentence reply to it? Well, let me try and sharpen it. Is quantum mechanics going to turn out to be the key to understanding consciousness? What about that? Tony?
I think well, obviously, insofar as brains do involve a lot of biology and biochemistry and so forth, and in the last resort, biochemistry is based on quantum mechanics, then in a rather trivial sense, yes. But I think a much more interesting question is, are the characteristically bizarre features of quantum mechanics, like the sort of Schrödinger's cat-like aspects, like the aspect we call entanglement and so forth, are these likely to play a role in biological phenomena? And I think right now there's somewhat of a schism in the physics community about this. There is a group of people who I suspect are probably still rather in a minority, but a substantial minority, who feel that yes, it's very likely that some of these weird quantum mechanical effects will play a role directly in phenomena. I don't say an explanation of consciousness, because I think that's a huge question. But in, let's say, issues of brain biochemistry which might be relevant to the explanation of consciousness eventually. So I think that's a minority point of view, but it's still a relatively substantial minority.
Yes, François, you want to say something?
Well, I would like to say that I don't believe that quantum mechanics will give a hint for the moment about the problem of consciousness. I mean, in that sense. The point is that I think that we, of course, do not even know how to define consciousness, so that's the first problem with it. And,
but let's not start now. Let's not attempt that now.
No, we don't know how to define it, but we may imagine some effects, which is also not so easy to define, like free will or things like this, which is essentially something that might be related to what we think to be consciousness. And it seems to me that, after all, that problem should be related essentially to determinism. And determinism in quantum mechanics is total in the sense that the wave function is totally determined. Even it's more deterministic, I would say, than classical theory. That's my opinion. But
that will confuse a lot of people in the audience.
Maybe, but then, no, I mean, there is something that evolves.
Well, I know what you mean.
Totally, completely determined. Well, you know that. And yeah, so I would think that in order to eventually have something that could perhaps be related to consciousness, the first thing in the realm of quantum mechanics would be a breakdown of probability. That might be an indication.
Right, thank you.
Yes, I'm going to make a slightly irreverent comment about this. Of course, your question wasn't only about quantum mechanics, it was about physics generally. Could it explain consciousness? We really await some definite outcome of these many discussions. And now it's quantum mechanics. There have been different fashions. There was a time people thought maybe the brain is like a computer. And I remember a few years ago, people started to think about neural nets and whether this was implicated somehow in the brain. And there was a very wise comment by one of the inventors. He said, physicists, having failed to use their brains to understand neural nets, are trying to use neural nets to understand their brains. So it is with quantum physics.
And the final word should go to Yakir, if you have anything to say on the subject of consciousness. I know you do, and I suppose a quick answer might be read my book, but I'll let you have the final say.
Could you tell me again
Well, the question is consciousness fundamentally a quantum phenomenon, other than in the trivial sense that, of course, we need quantum mechanics to describe atoms, and the brain has got atoms in it?
Well, there is first of all a question whether there is any indication that some processes that happen in the brain that are relevant for our thinking are quantum mechanical or not. And although Roger Penrose, for example, claimed that that's the case, I think experimentally there is no evidence that there is something that's really important that's quantum mechanical. On the other hand, I think that we don't even understand what conscience is in order to be able to answer this question. So as long as we don't know what conscience is from the point of view of physics, we know each one of us experiences that we have a conscience, but we don't know what it means, then it's very difficult to ask for physics to explain what it is before we know even what we are talking about.
Right, so before I bring the evening to a close, and we thank the panelists, it's clear that events like this don't just sort of happen spontaneously. They require a huge amount of effort and organization. And I certainly would like to thank Jeff Tollockson, who has put in a lot of work, not only dragooning the panelists into agreeing to do this, but also into organizing the logistics. And of course, thanks to Chapman University for hosting this occasion, not only the discussion this evening, but the conference which is to follow. And so, last but not least, I think a round of applause for all of our panelists, but most especially Yakir Aharonov, in whose honor we are gathered here this evening. And that's it.
Okay. Don't fold
I wrote it, but I need.